So the next protocol is ESP. ESP is provides everything: confidentiality, authentication, integrity, anti-replay, even traffic flow confidentiality, limited traffic flow confidentiality. So traffic flow confidentiality, I think we have discussed this before, but let me just explain again, is that you don't want people to know how many packets I sent. So I may send some packets which have no information in them, or I may make the packets bigger than what they are, right? So you cannot just say, well, this is only a short one-word bomb. It could be big message. So that is allowed by this, and the technique is very simple, basically by having padding. Services depend upon the option selected when you establish security. And net location can use a variety of encryption authentication, and rest of it basically it specifies all those algorithms for those. So the packet itself starts with SPI, sequence number, initialization value, IV. Now this is different from ICV. ICV is here, IV. Yeah, see, when you do encryption, you remember the block mode encryptions, and you were doing chaining, then you want to start from the beginning, that is the IV. Alright, payload data, and they decided to put the next header at the end. Can you believe this? And the ICV is at the end. So anyway, the next header is not up front, it is at the end. So this is the payload type. They get the whole packet, then only they can process it, so it doesn't matter where they put this stuff. But generally we expect to see things in the front, but here in this protocol they have the next header here, pad length is here, padding is there, and then TFC padding. So TFC padding is the traffic flow confidentiality padding. That is the padding you put simply to extend the length, not because you want to make it a multiple of 64 or 32. The second padding is to make it multiple of whatever. Actually, it looks like it is multiple of 256, because you can have a padding up to 255 bytes. First of all, the payload starts from here. This is where the IP header might be. If you have put the original IP header, internal IP header, that will be right there. And the original IP packet's end will be here. So that is the original IP packet. If there was no header, then the original IP payload will be there. All right. Second thing is, you should notice these things on the side. It says payload is from here to there, right? So that is your question, was that why the IV is part of the payload? Is that the question? Oh, okay, all right. That is actually, a misdefinition in my view, and this is my personal view. I think this is really the thing that came from the higher layer, which is the IP layer. In this case, the higher layer is IP layer. And so that should be called the payload. This was added by this header, this layer. So to call this payload is not, and similarly to call this padding as a payload is just arbitrary in my view. Actually, really the payload is this. And the thing to notice is that all this part is encrypted. Figure in the book has this wrong color for this one. You see, IV cannot be encrypted, right? You need IV for decryption. So it says here encryption, and the arrow ends here. So this is not encrypted, but when the color person made a mistake here in coloring this thing, it should be clear. So the IV is not encrypted, and in my view, this would be called the payload, but the padding and the IV would be part of ESP, strictly speaking, but the book has the arrow indicated here as a payload. But really, this is the payload. Next header, okay, now pad length in bytes, and then the next header is TCP, UDP, whatever. Authentication data includes ICV. There are several errors in this diagram, let me tell you. I'm noticing another error. This arrow, ICV coverage, has to go up to here, because ICV always protects itself. CRC always protects itself. Okay, you cannot design an integrity check value where you can change the integrity check value. Right? So if I were to redraw this diagram, I would not put a color here. I would make this arrow bigger. This thing looks okay. The payload I may have to change unless I want to start calling this padding as a payload, which could be acceptable somewhat, but to call ID as a payload is not acceptable. It is not to me. But this is how the picture is in the book. All right, moving on. ESP version 3 again came out in 2005, and again solves almost the same problem: unicast versus multicast. Extend the sequence number, put the mandatory algorithms, and then if you want to get both confidentiality and integrity, so then it allows that combination. And then traffic flow confidentiality was added in version 3, the TFC padding. Can generate and discard dummy padding packets. Next header is equal to 59. So if the whole packet was the TFC padding, then the payload is 59. Everybody understood that statement? Is that there is no TCP IP or anything here. It is just TFC. All right. Issue: no version number in the header, but older versions will reject new algorithms and options. So there is a problem still that neither of the two, AH, I didn't see in the AH also the version number, and ESP does not have a version number. So when you get a packet and it is version 3 and you are at version 1, what do? I mean, you just think that the packet is misinformed or misformed. For example, the older version may not know TFC business, or they may not know that number there was 59. They may not know what to do with it. So actually throwing it away is not a bad thing, but it just happens to be coincidental. There could be some options that may not be correctly done. All right, so how do we do anti-replay? Anti-replay, as we said, is that you keep a window from beginning to the end that you will accept. And you decide that, well, we'll keep a window of 200 packets. So even though this is the packet I got, and I'm going to, and this is the next one I'm expecting. But if something comes ahead of time, I will take these packets. And if something comes again from behind, I will take those packets. But anything before that, actually, we will throw away. So now let's see. And the window is advanced when the valid packet is received. So we have valid packets up to here. Sorry, it's not here. We have up to here, and we will take any of the next 200 packets. And if something comes up, and then the window may move up to whatever valid packet you have received, so that there is no gap. So if suppose it's up to here, you get this one, you might move up to this one, because you have received all of these. Just like the flow control window, this is the anti-replay window. And so you just keep a fixed size window, and you move it as soon as you receive valid packets, and so that everything before that is valid, already received. If you receive anything out of the window, you throw it away. If you receive any older packets, you throw them away. If you receive any packets which are too far in the future, throw them away. So these packets are kept out of order in some sense, is that these white spaces are still not received, and these out of order packets are being kept to hoping that we will get them, and then we can move the window up. At some point you might time out and you might get a retransmission or whatever. All right, so that is the anti-replay service. This is homework on anti-replay service. So basically the key is up to here we have received everything, and we therefore will accept the next W packets. We'll keep them out of order in cache. If anything comes after W, we don't have a space to keep them, so we'll throw them away. If we receive something old, we don't need them, so we throw them away. All right, so now combining security association. So you can implement AH or ESP, and you can also implement both AH and ESP, but you will have to somehow put one inside the other. So you have to make a bundle. And actually, maybe I should show you the next picture, which shows the bundle clearly. So you could have one tunnel, and inside that you have another tunnel. Inside that you have essays. So you could do a association bundle, and you could have AH over ESP, or you could have iterated tunneling, where these are the 4 cases just shown in the next picture. So basically, all security is within the end systems, all security is between the gateways, and then case 1 is inside case 2, and then the tunnels between the remote host and firewall, and 1 or 2 essays may be in case 1. So there are 4 cases which are shown here. So first case is this one, case 1. You have a host, and this is end to end, and you could have many SAs which go through this tunnel or this bundle, and so that is called case 1. In the case 1, you have end to end security. It could be AH transport, or ESP transport, or ESP inside AH, or any one of these 3, AH, ESP, or ESP inside AH, or ESP. So this is basically one inside the other, but everything is end to end. So this is a straightforward, simple thing. You could keep putting the tunnels inside the tunnel, which means that you can keep putting headers on the headers on the headers on the headers, end to end. So that is case 1, which is simpler. In case 2, the tunnels end at different point. So this tunnel ended here, whereas this tunnel continued to the end. So case 2, between the gateways or firewalls, single association, no nesting. This is the second case, between the gateways. Sorry, case 2 is here. Sorry, I cannot even read very well. These letters are so small. Case 2 is here, between the gateways. Case 3 is this one, where you have nesting. Case 3 is 1 inside 2. Case 1 end to end inside case 2 between the gateways. So that is case 3. You have gateways as well as end to end. Case 4 is tunnel between a remote host and firewall. 1 or 2 essays may be used as in case 1. Now this is the most general case, is that you have some end to end, you have some tunnels, and so on and so forth. So this is a combination of all 3. This one is all end to end, this one is all gateway to gateway, this one is gateway inside the end to end inside the gateway, and here the mixture is different than that one. So I don't know, actually. I think that basically the idea is that you could be having multiple levels of headers, and they could be ending at different points. They should have simply said that rather than combining these 4 cases, but that's what it is. All right. So, so the summary of this slide and the next is that you could have tunnels inside the tunnel, ending at different points. Okay. Now we come to the key management, IKE. So the purpose of IKE is handshake, to just somehow agree on a security or a secure key, and so basically we need 2 pairs of keys. We need 2 keys for one direction, 2 keys for the other direction, and why you need 2 keys? Because we need 1 key for integrity and 1 for confidentiality. So they use separate keys for integrity, which requires hashing, and confidentiality, which requires encryption, right? So we use different keys. So we need 4 keys for a 2-way connection. Now the key management could be manual, in which case it's not a big deal. You could send somebody the key by mail, by some other method, and or could be configured. But what is more interesting is this automated key management, where you can do it remotely, and so that's what we are going to talk about. That's what really the IKE is all about. So now there are few names that you have to understand here, and you will see them all over the literature. One is called Oakley, and one is called ISACamp. So Oakley is the name of the key exchange method, and ISACamp is the name of the key management method, and these are all historical. Historical in the sense that before IKE was there, or IKE version 2 was there, they had this Oakley key exchange and ISACamp key management, and then IKE version 2 came about and they removed the names, but they use the same techniques. So every book that talks about IKE has to talk about Oakley and ISACamp. Even this book talks about Oakley and ISACamp, but the previous book that we used in this course only had ISACamp and Oakley. Oakley is the Diffie-Hellman key exchange. If you remember, the Diffie-Hellman key exchange had some weaknesses because it could not identify the parties. The middle, somebody in the middle could just, may attack. So the man in the middle attack. So that is removed. And denial of service is removed by having cookies. And then several groups of pre-specified global parameters. So what is that? Basically, when you want to do Diffie-Hellman, if you remember Diffie-Hellman now, you had a G number, G, which was the global number, and you raised it to some power, and you sent that value, right? Nobody can determine the power because nobody can take the log. But everybody knows G, and everybody knows G raised to A, whatever number you selected. Right? So that G number is a big number, and so how do you find that number? Well, everybody could go and try to factor out lots of numbers and figure out a prime number, but instead of doing that, what the world has done is they have agreed upon a certain number values, certain values. Everybody uses those values. Okay? So if you go to the RFC, whichever RFC this one talks about, it has 5 or 7 possibilities. Okay? If you want to use 512 bits, use this G value. If you want to use 1024, you use this value. If you want to use 2034, use this value. So that is what it means by global parameters. So that actually makes it weaker. If everybody is going to use one global, then you don't have to worry about trying out different things. But I'm not sure as to basically what is required to break a 512-bit thing like that, right? But having it random would be much more stronger, I think, than having a global value. So maybe people can just sit down and just break that and make a whole table of all the powers of all of those numbers, which will be a big table. But anyway, so that is the pre-specified global parameters. Nonsense to protect against replay. So that adds nonsense. And then DH public key exchange with authentication using digital signatures, public key encryption, or symmetric key encryption. So you can even use public key encryption, which means you could use certificates and things like that, to including symmetric key encryption if you already had symmetric key. And so somehow you basically exchange the keys. Can use arithmetic in prime fields or elliptic curve fields. So they use both. We saw the RSA, which was arithmetic in the prime fields, and we saw elliptic curves. Remember elliptic curves? To add 2 points, you had to do all this math. So all that is used here in real world. Alright, so Oakley is Diffie-Hellman in very simplified manner, okay? Because it is an extension of Diffie-Hellman. Next is ISACamp. So ISACamp stands for Internet Security Association and Key Management Protocol. And it basically provides what to do to create new associations. So this is a protocol. And so it defines the procedure and the packet formats to establish, negotiate, modify, and delete security associations, SAs. It is independent of the key exchange protocol, encryption algorithm, and authentication method. So basically you could use any exchange protocol such as we talked about, public key, private key, whatever, but it has certain protocols, certain messages that have been formalized. So for example, you could send a header message get a header response, and so on and so forth. At the end of this, these two messages, you will have a security association, and then you can create child security association. Is that you could create, once you have one secret established, then you don't have to go through the previous negotiation, because you already know what encryption algorithm you are going to use. All we need to get a new key. I could just pick a new key from my pocket and send it to you by encrypting it, because we have a shared secret. So creating the child message is much more easier. So in which case you just send those two messages. If you want to create the first SA, then you have to go through more what we would call the initiation, which means Diffie element kind of thing here in the beginning. So there's initialization, and then the first SA, and then the child essays. Like the details actually you can read in the book, and so what these different fields are, I don't think I want to go them here though. I mean, like basically the standard method of agreeing on a key. So the I packet format, SPI on two sides, next payload, rather than next header, major version, minor version. So now here they remember the version numbers, exchange type, flags, message ID, and the length, and they don't say what the unit is. So anyway, there's a length of the message, and message ID is the sequence number. So this is actually the sequence number, and exchange type is the message type. So this one will tell you whether this is a header message. So these messages are different types, and it is not indicated in this picture, so I can't tell you. But basically, that goes here. The message type goes here, and this is just a sequence number. The message types could be key exchange, could be identification, could be certificate, could be a certificate request, could be authentication, and so on and so forth. So these are all different message types. All of them have a number which I have not indicated here, or the book has not indicated here. But basically that number, exchange type, goes in that field that we saw a minute ago. And the key is that there are two words they use. One is called a proposal, and one is called transform. So you send a set of proposals for encryption, for hashing, and so on and so forth, and that's why it is a set. And obviously the response would come out, a selection of that. If it is a key exchange message, then it will contain the Diffie element group number. So that is the global group number. Remember we talked about there are 7 or 8 group numbers specified in the RFC. So you will put that this is the group number I am taking, and these are all the data required for generating the key. If it is an ID, then it will say what type of ID it is, IPv4, IPv6, and whatever the ID is. Certificate, it will have what encoding the certificate data is in, and then the certificate itself. Certificate request, this is the encoding I want, this is the authority I want. Authentication, and so on and so forth. So basically, I mean, there are many things which go on in these messages, and so the exchange type field is this. Now these are the algorithms which are required for which are allowed for encryption: 3-CBC and AES CBC, and there are two different sets, BPN-A and BPN-B. BPN-A is older, BPN-B is newer and stronger. So in the old days they used this, and now we will prefer these. Similarly, for the suite, the cryptographic suite, that means the combination, there is something called NSA suite B. So NSA has specified set of combinations which is, there must be an A before, but now it is B, which is what is used for the government use, and that specifies these combinations for integrity, for encryption, for pseudo-random functions, and so on and so forth. So these are all the algorithms that are specified in that set. That brings us to the end of this IPSec chapter, and the 7 things that TAR, first of all, that IPSec is at the IP layer, and it provides authentication, confidentiality, and the key management. And since it is the IP layer, it applies to all the traffic, all protocols, all transport protocols. Second thing we learned is that the security sessions are one way. So the reason they are one way is because the direct requirements for the two directions could be very different, and that they can be bundled one inside the other. Authentication header is done using integrity check value, which is done using HMAC. ESP uses confidentiality and integrity both. Then the SAs can be tunnel or transport. So now let's just remember, transport means end-to-end. Okay? And so that is what can be done. End-to-end means that the original IP header is not required. Then in the IKE we learned two words, Oakley, which is the defilement part of the IKE, and ISACAM, which is the protocol negotiation part of IKE. That's all. So there are two parts, two homeworks. Two parts homework. Actually, both are very small. Actually, it turns out. One is for each field of IPv4, indicate whether it is immutable, mutable, predictable, and so on and so forth. And second thing is about the window. The replay window spans from 60 to 24. What will happen to packet 50, 100, and 150?